Cool. Okay, our second speaker for today is Cheng Guo. Cheng is a fourth-year PhD student in operations research at the University of Toronto, where she's working with Merve Boudour on various topics around integer programming, modeling, and algorithms with application to engineering type problems. And today, Cheng is going to tell us about copositive duality for discrete markets and games. So please go ahead, Cheng.
Okay, thank you, Elias, for the introduction. I'll do the full screen. Okay, so hi everyone. Today I'm going to talk about copositive duality for discrete markets and games. This is a joint work with my PhD advisor, Merve Boudour, and also with Josh Taylor. Both of them are professors at the University of Toronto. The starting point of our work is this concept of economic equilibrium, where we have a balanced and a stable state for an economic problem. For example, if we have a market problem, then we have this concept of market equilibrium, where supply equals demand, and we also have individual rationality, which means individuals in the market do not want to deviate from the equilibrium. Here is a picture of the example for market equilibrium in a perfect market, where the equilibrium point is represented by this price and quantity set of $1 and 15 chocolate bars. And at this point, the supply and demand matches, and no one really wants to deviate from this point. Some of you might be familiar with this concept of Nash equilibrium in game theory, which means that in the game, no player wants to deviate from the equilibrium. Also, we have this concept of wardrobe equilibrium, which is a Nash equilibrium with each player being infinitesimal, and this is often used in traffic networks. So if we have a convex economic problem, the equilibrium is commonly obtained through strong duality. For example, if we are doing pricing in convex markets, then we can directly obtain the shadow prices in convex optimization problems. And this price is guaranteed to be a price for the market equilibrium. Similarly, if we have a game and each player in the game are trying to solve a convex optimization problem, then there are well-established existence and uniqueness theories for the Nash equilibrium. And also we can use Crash-Kuhn-Tucker or KKT conditions to calculate the Nash equilibrium. However, in practice, there might be non-convexity in the problem, like you might have discrete decisions and the problem might be modeled with mixed integer programs or MIPS. As we know, MIPS generally do not have strong duality. We do have the concept of Lagrangian dual, but it's not a strong dual. And for the subadditive dual for MIPS, it is a kind of strong dual, but its analytical form is hard to obtain. So this creates problems for example, markets with discrete decisions because it's hard to get equilibrium prices. This problem is a kind of very important problem in electricity market literature, because in electricity market, we have decisions about starting up and shut down of power generators. And in such market, it's hard to get equilibrium prices. So there is a large literature in this field about how to derive pricing schemes. For example, the first pricing scheme, restrict pricing or RP, is widely used in the US energy markets. And both the first one, RP, and second one, primal dual pricing, are based on the idea of getting a shadow price of the linearization of the MIP formulation. While the third pricing scheme, convex Hall pricing or CHP, is based on the Lagrangian dual of the MIPS. Also in games, we might also have discrete decisions. For example, the players might be solving MIPS for their optimization problem. And the literature of the discrete game usually focus on the algorithm side. And as far as we know, those algorithms only deal with pure integer problems. Also, as to the best of our knowledge, we do not really have theoretical results for general discrete games in this literature so far. So how do we deal with this problem? In our work, we are try to reformulate MIPS to an equivalent convex program called copositive program. And convex programs do have strong duality. So we are using this relationship to apply to discrete market problems and discrete game problems. In what follows, I will first introduce some key concepts of copositive programming, and then I will talk about our two applications. So the count for copositive matrices is defined as follows. This definition is similar to the definition for positive semi-definite count, except that in the positive semi-definite case, y would be a real valued vector instead of a positive valued vector here. The dual count of a copositive count is called a completely positive count, where it is defined as follows. If we have a completely positive matrix, it can be decomposed as a product of a positive matrix and its transpose. Again, it looks like the Cholesky decomposition of the positive semi-definite matrices, except in that case, X will be defined differently. In addition, if we define positive semi-definite count S plus, and also define this count N for matrices of element-wise non-negative matrices, then there is this relationship from Parillo's PhD thesis, which says that the Minkowski sum of S plus and N is a restriction to the copositive count, and the intersection of S plus and N is a relaxation of the completely positive count. In our work, we are using this classical result for mixed integer quadratic programs, or MBQPs, which is a generalization of MIPS with quadratic objectives. So this result says that MBQPs can be reformulated as completely positive programs, or CPPs. So what is a CPP? A CPP is a linear optimization problem over a completely positive count. And the dual problem of CPP, which is called a copositive program, or a COP, is similarly defined as the linear program over a copositive count. So CPPs and COPs are usually solved by semi-definite program approximations using Parillo's SDP hierarchy, as we've seen in the last slide. Here's the picture to summarize this relationship between MBQP, CPP, COP, and their SDP approximations. So let's take a closer look at this classical result for MBQP. We start from this non-convex problem of MBQP, where we have a quadratic term in the objective, which this quadratic term might as well be non-convex, and we also have binary decisions in the problem. So this non-convex problem can be equivalently reformulated to the convex problem on the right, where we basically just replace the quadratic X transpose term here with this big matrix X, and we also add a couple of more constraints to link small x and capital X. It's worth noting that the quadratic terms and the binary terms are the terms that bring the complexity in the non-convex formulation, and those non-convexity all come into this conic constraint. So except for the conic constraint, this convex problem will always be linear in the objective and the constraints. And here is a picture to summarize what we are doing in this work. We start from a non-convex problem. We are reformulating it to a CPP, which has strong duality. And we are using this relationship for first discrete market problems, where we derive a COP-based pricing scheme. We're also using this relationship for discrete games, where we derive existence and uniqueness results for Nash equilibrium, and we also derive KKT conditions for calculating the Nash equilibrium. And because we are solving copositive programs in both of the applications, we further propose a novel cutting plane algorithm for COPs. Our contributions include proposing a notion of duality for discrete problems. Also, we propose a novel COP-based pricing scheme for non-convex energy markets, where this pricing scheme is revenue neutral and under certain conditions is also individually rational. We also propose several new theoretical results for mixed binary quadratic or MBQ games, which is a special case of discrete games. In addition to the existence, uniqueness, and KKT condition we obtain for the Nash equilibrium in MBQ game, we also formulate a KKT condition for a special type of MBQ game as a single COP problem to make the calculation easier. Finally, we propose an exact cutting plan algorithm for mixed integer COPs, which we believe is the first in the literature. Let's look at the first application in non-convex energy markets. So why do we care about pricing problems in energy markets? And we care about it because energy market models are widely used by private companies and policymakers to make operating and investment decisions, as well as environmental and energy policies decisions. If we have a good market design in the market, then we should be able to efficiently match the demand and supply, which means we should not have oversupply or undersupply of the goods. However, the current pricing schemes in practice are unable to recover the total costs of the generators in the system, which creates a so-called missing money problem. As a result, the owners of the generators do not have the incentive to invest in necessary new generators. We are formulating this MIP for the energy market problem, which is called the unit commitment problem, or UC, which is standard in the energy literature. And in this problem, we decide on the P, the production levels of the generators, U, binary decisions for turning on the generators, and Z, the on and off statuses for the generators. In the MIP, we are minimizing the overall cost of production and turning on the generators. We have a demand constraint over all the generators, and we also have a generator-dependent operational constraint in this generic form, which include capacity constraint, production level constraint, and ramping up and down constraints, for example. Also, we only need to enforce Z to be binary, because if we have Z being binary and we have those operational constraints, then U is automatically binary. Also, what's noting here is that if we had a linear program as our UC problem, then the price can be, the electricity price can be simply obtained as a dual variable for this demand constraint lambda t. However, we do not have a linear program here. We have a MIP here. That's why we cannot get the price simply as a dual of the demand constraint. What we are doing is to reformulate this UC problem as this following CPP problem, where we have additional constraints for the lifting constraints and the conic constraint, and the dual variables for those constraints are in the parentheses here. And the dual problem of this CPP is a COP problem. And it's worth noting that we are using the dual variables appearing in the objective of the dual problem in our pricing scheme. So in our pricing scheme, we are using the shadow prices lambda t, capital lambda t for the demand constraint, and also the shadow prices phi and capital phi for the operational constraints. More formally, we are defining this copositive dual pricing, or CDP mechanism, that uses the optimal solution from the dual COP problem. Under this mechanism, at each hour, the system operator, by the way, the system operator or the utility is just this agent that coordinates the demand side and supply side of the market. So the system operator collects payment from the demand side and pays the supply side, pays the generators. So the system operator collects this much amount of payment from the demand side or the load. And this payment consists of the payment for the demand and also the payment for the operational decisions. In addition, the system operator pays each generator G this much amount of payment. So this payment consists of the payment for the production, the payment for the operational decisions, and the payment that's related to other generators' production levels. So this last payment is related to some lifted constraint in our reformulated problem. Thanks to the strong duality of CPP, we are able to prove that for system operators, they are budget balanced, which means that their revenue from the demand side equals their payment to the supply side. In addition, we are able to prove that for generators, their total revenue equals their total cost, or they have revenue neutrality, which means they are not losing money. Also, we prove that under certain conditions, we have individual rationality in this problem. However, there are also some drawbacks. For example, the revenue neutrality only holds for the aggregated level. It does not hold for individual generators. Also, in this pricing scheme, we are using fee and capital fee, which depends on each generator. And we do not want this in our market because in real life, we do not really care about which generator produces our electricity. We only care about a uniform electricity price. That's why we also propose this revenue adequate CDP or RCDP scheme, where based on this dual COP problem, we add revenue adequate constraint for each generator to ensure that for each generator, revenue will exceed the cost. And we are able to do this because we have direct access to the pricing problem. This is a unique property to our idea of this reformulation and duality, and other pricing schemes in the literature do not really have direct access to the pricing problem. Next, I will talk about our second application of mixed binary quadratic or MBQ games, which is a special type of discrete game. So one example of MBQ games is this classical bimetric game. Here is an example for bimetric game called Prisoner's Dilemma. And this is a discrete game because we are making discrete decisions about confess or not to confess. Another example of MBQ games is this Kuno game in energy markets where where competing generators are deciding how much electricity they are going to produce. The setup for the MBQ game is that we have n players in a system in a set of I. Each player has a decision vector of xi, which might contain continuous variables and also might contain discrete variables. And the feasible region of xi is denoted by this big xi here. Each player is solving a MBQP problem as follows. And let's denote the objective function as this payoff function fi. Then we can define the pure strategy Nash equilibrium x star as follows, which just means that for each player I, they do not have the incentive to deviate from this equilibrium point x star. Similar idea, we are reformulating this optimization problem MBQP as a CPP problem. And as a result, we can also transform MBQ game as a CP game where each player are solving a CPP optimization problem. We can prove that under certain conditions, the Nash equilibrium of an MBQ game is equivalent to the Nash equilibrium of a CP game. That's why we are able to get the existence and uniqueness results for the Nash equilibrium in the MBQ game. So here are like several conditions here. Some of those conditions like 1, 5, 6 are directly inherited from the existence and uniqueness conditions of the convex games. And other ones of the conditions like 2, 3, and 4 are unique to our discrete case because we need to reformulate our discrete game to a convex CP game. We also get the KKT conditions for our MBQ game as follows. However, this KKT condition contains bilinear terms, copositive conic terms, and the completely positive conic constraints, which is very hard to solve. Luckily, for a special case where MBQP problem contains only binary variables and all equality constraints, for example, by the way, this is not a trivial case because bimetric schemes belong to this case. And if we have those conditions, then we can reformulate these KT conditions into a single mixed integer COP problem, which is much easier to solve. So in order to solve this mixed integer COP as well as the COP problem in our pricing application, we propose this cutting plan algorithm for COP, where we deal with this general mixed integer COP formulation. So to solve this, we are removing this conic constraint. So we have a relaxed master problem. And to strengthen this master problem, we are solving the following me problem as a separation problem. So basically, we are taking an optimal solution for omega from the master problem and put it into a separation problem. And if the objective of separation problem is not 0, then it means that this omega hat from master is not a copositive program. Then we need to add the following cut into a master problem to tighten the master. So this algorithm is exact when terminate, which is different from the commonly used SDP approximation, which is an approximation. Also, this algorithm is purely MIP-based and straightforward to implement with Groby or Cplex, while there is this method called simplicial partition in the literature for copositive programs, which is relatively hard to implement. In addition, this algorithm is applicable to mixed integer CLPs, which we believe is the first in the literature. Here are some enhancement ideas for the algorithm. I won't go into the details. We try some of them, and some of them are helpful. For numerical experiments, first we compare our cutting plan algorithm with this commonly used SDP approximation in the literature on this max click problem data set. And we find that our cutting plan algorithm converges usually in a few iterations for this problem. And sometimes our method is even faster than the approximation method. We also test our COP-based pricing scheme on those classical non-convex market example, scarcity example, and also on a California-based energy market dataset. We are comparing with the restricted pricing and convex Hull pricing in the literature, and we find that our RCDP pricing scheme does not really need any uplift payments, while those pricing schemes in the literature do need those payments. We also tested our KKT conditions for discrete games on the biometric games, and we find that in all our testing set, our algorithm converges in a few seconds. As a summary, we propose a notional duality for discrete problems. We also propose some novel theoretical results for discrete market and discrete games problems. And we also propose an exact cutting plan algorithm for mixed integer CLPs. Some of the future directions we think are interesting include that to apply this scheme to some other economic equilibrium problems like traffic problems or matching. And also we can further simplify the CPP reformulation, like allow some inequality constraints in the CPP reformulation, and also remove some redundant constraints to make the calculation more efficient. And also we could further improve on the cutting plan algorithm. So here are my website and email address. Feel free to contact me if you have any questions. Also, we are trying to submit this paper and make it online by the end of the month. But if you are interested in the paper before that time, please shoot me an email and I can send you a recent version of the paper. Thank you.
Thank you very much, Cheng.
Mm-hmm.
Any questions from the audience for the speaker?
Can I ask a question?
Sure. Hi, Weijun.
Hi, this is Weijun. Yeah. So first of all, very nice talk. So I see you know every year you are doing very different things, and every year you have each time I see your talk, you know, it's a very interesting work. So
Thank you.
Again, this is another interesting work. So I'm just curious. So for this, you know, for MIP, we can also have, you know, augmented Lagrangian dual, right? Which is exact. So why don't we directly use augmented Lagrangian dual instead of using copositive, which is, I guess, you know, copositive is more difficult to solve, right?
Augmented Lagrangian, I'm afraid I'm not too familiar with that concept. Is it easy to get the analytical form for that dual?
It's not. So maybe we can talk about this later. So it's like, you know, you penalize the constraint. So first of all, you do the same Lagrangian.
Yeah, it's a Lagrangian dual.
Yeah,
yes.
And then you have additional penalty term for this quadratic penalty or some other penalty, you know, of the constraint.
I see.
Yeah.
I see. And I think it might be efficient computationally, but I'm not sure if it's good for the theoretical analysis, because you have this penalization term and you might need to tune it, I guess, in computation process. But here we are trying to also get some like theoretical results after the reformulation. And it's good to have a neat analytical form of the dual. And CPP and COPs do have this advantage because we have a well-defined analytical form for them.
I see.
But I think that's definitely an interesting idea. I think I'll talk to you further about this idea. I'll also look into the literature. Thanks for the question.
Thank you.
Great. Thanks for that, William. So in the interest of time, we'll move to the next speaker. Thanks, Cheng.
Thank you.